Okay, notice I have here an outline of what we're doing today. And at the bottom, I have highlighted PTQs and box numbers. PTQs is to remind me and you that starting today, should have been starting last class period, but I forgot. I need you to turn in a potential test question that's based on material given during the lecture. Okay, the box numbers, there's a place for box number on the form I gave you. The box numbers, I will give them to you on Monday because I did not think about, well, I didn't think that I was going to need to use them until I realized, wait, with all the PTQs, I really need the box numbers. The boxes are right on the other side of the wall right here. And so after we have scanned your PTQs, after we have scanned your lab reports, etc., we'll put them back in those boxes. So everything is scanned and returned to you graded on Moodle, but we'll return ungraded stuff back in there. Just want to make sure it's clear. When you get stuff and it's ungraded and you're like, but it's ungraded. It should be graded on Moodle. So everybody understand PTQ today? Question based on today's lecture, right? Monday we'll worry about the box numbers. This is the slide we had at the end of last class period. This just reminding us that mass is a different thing from weight, but they're related because the weight is proportional to the mass, but the proportionality depends on the acceleration of gravity. So if you go somewhere with a different acceleration of gravity, your weight will change while your mass, which is how much of you there is, won't change at least as rapidly. So the acceleration of gravity, believe it or not, is not constant on Earth. You weigh more different places. The Earth, because it rotates, is oblate. The equator is a larger radius than going pole to pole. As a result, the acceleration of gravity is lower on the equator. So if you're on the equator, you weigh less than if you're at the pole. Good to know, right? Easy weight loss tip. Move to the equator.
How much?
Well, it's not very. The difference between the highest and the lowest acceleration of gravity on Earth is something like from, 9.75 to 9.86 or something like that. So it's a small variation. Okay, and then we had this slide talking about equilibrium. Equilibrium what does the word equilibrium mean? Okay, that is a correct meaning for it. I'm thinking the literal meaning. Right, so that's correct. Don't say, oh no, bad answer. What's the literal meaning? What does EQUI mean? Equal, they're the same. And what is the librium? What does that aspect mean?
Velocity.
Not velocity. It's, remember that we used LB for our abbreviation for pound. The librium stands for force. A pound is a unit of force. So what is a force? Anything that pushes or pulls. So equilibrium means equal forces. We so often make the mistake of thinking equilibrium means at rest. If something's at rest, it is an equilibrium. But if it's moving at a constant velocity, it's also an equilibrium. Because it has to do with equal forces. And so in the case that's shown here, this young lady is pushing, I don't know what, I just remembered I forgot to bring my demonstration. I'm gonna have to make do with things at hand. Won't be as fun, but it'll work. That's for later in the lecture. She's pushing this table at constant speed. If she's pushing the table, first of all, is she applying a force to the table?
Yes.
If it's moving at constant speed, what do you know about the forces? It's an equilibrium, so the forces have to be adding up to zero. You have equal forces in opposite directions. So she's pushing this way, What else do you know has to be happening on the table? Well, the table's pushing back, that's Newton's third law. But there's something pushing the table back at her with the same force. And what would that be?
Gravity.
Not gravity. Gravity is in the vertical direction.
Friction.
Friction. So we know the force of friction is exactly equal to the force she's pushing if she's moving at constant speed. If she doubles the speed and goes at constant speed, the friction is going to still be balancing her. It's not dependent on the speed. If she's going at constant speed, the force of friction is going to have to balance the force she's putting on it. So, in which of these cases is a bowling ball at rest? And notice you have the first one, the second one, both or none as options.
C.
Okay, Jessica with a strong C. Anyone else? I haven't even looked at the answers, by the way. I don't know if you're right or wrong. I will read it.
I'm always ready to learn.
Jessica's always right. Well, this is good. Everybody just... Okay, well, no one else is going to contradict Jessica, so let's look at it. If it's at rest, the question equilibrium is constant motion, right? Equilibrium is going to result in constant motion. So if it's at rest, is its motion changing? Yes or no? No. So that means it's a constant rest. So A was definitely in equilibrium. B, moves steadily in a straight line path. Is its motion changing if it's moving steadily in a straight line path? Nope. And so Jessica was absolutely correct. Both of them are equilibrium. Yeah, are you saying C told you I'm always right? Yeah, good job. Okay, now we're going to introduce some other forces. To try to make life easy on you, our textbook author uses the term support force. In any other physics class, we use the term normal force. Here's why he chose support force instead of normal force. If I say normal, what does that mean to you?
Average, like nothing really happened.
Okay, average we had from two people, nothing really happening. That is a correct definition, but it's not the mathematical definition of normal. Normal means something else in math. Normal in math is the multidimensional version of perpendicular. And so if you have a line, a normal to the line, well, perpendicular to the line is a 90-degree angle, right? If I have a table, the table is a two-dimensional, the tabletop is a two-dimensional surface, and the normal to the tabletop is the direction coming straight out of it so that it makes an angle of 90 degrees with the tabletop in any direction. And so that's what the normal force means. And that's why the textbook says support, because what's keeping me from falling through the ground? It's the ground pushing up on me. It's the normal force, but it's supporting me, so I said, let's call it the support force. It's normally called, see, normal in the general sense, it's normally called the normal force. The normal is the direction. Go ahead.
So on like tests and homework, you want us to write normal or support?
You can use either one. But you're going to see, I mean, our textbook will always say support, but if you read anything else, it's going to say normal. And so it's, I think, important to know the standard word for it. So the normal force is the force that keeps things from breaking through a surface. So Amber has her drink sitting here. The tabletop is pushing up to keep it from falling through the tabletop. If I took it out here so the tabletop wasn't pushing up and let go, it falls. Why would it fall if I brought it out here and let go? Okay, there's no normal force, but there is. What did you say?
I didn't say.
Oh, I thought I heard somebody.
Support.
There is the gravitational force that's pulling it down. So out here, if I let go, it has gravity pulling down, nothing pushing up, and it falls. But here, gravity's pushing down, the table's pushing up, and it stays. Now, if I come over and I lean on the wall, my fist isn't going through the wall. That means that there must be, when I'm pushing on the wall, there must be a support force, a normal force pushing directly out of the wall to keep my fist from going through it. So another mistake students make in general physics a lot is they think that the normal force or support force has to be vertical. It's vertical from a horizontal surface, but if it's a vertical surface, the support force would be horizontal.
Does it just have to be directly opposite of the applied force?
No, it has to be directly out of the surface. The difference there is, okay, if I put my hand at an angle like this and push, there is a friction force going this way, and there is a support force going this way. If I add those two together, it's going to be directly opposite this force being applied. But we call them two different things. So obviously I see where you're coming from because that's the net result. So support force, how big is it? It's as big as necessary, up to the point where you break the surface and you no longer have the support. So support force, you never have an equation for it. It's as big as necessary, so you have to look at the rest of the forces to figure out what it is. Now this is a good one. Take you back to my little brother. At one point in time, my little brother was really heavy. And so he was going to have a surgery weight loss surgery. And before you do the weight loss surgery, you have to apply to get insurance coverage and whatnot. And he had to put down his weight. Well, you know what they don't do? They don't make bathroom scales that would measure my brother's weight. And so he's all like, okay, I got this covered. I'm just going to buy 2 scales and stand with 1 foot on each scale. Well, how do you determine your weight when you stand with 1 foot on each scale? Neither scale reads your correct weight. So how's that going to work? Let's start with the simple. If he's standing here and he's not accelerating, if he's staying stationary and still, we say in physics that he is in what state? Equilibrium, which means the total forces acting on him are 0. Well, he knows he has his weight as a downward force, and now he has 1 foot on each scale, so he has 2 support forces, 1 from each scale. The scale tells you how big its support force is. So how can he determine his weight from the 2 scales? Add them together, because you have the downward force has to equal the sum of the upward forces if he's in equilibrium. Guess what number he came up with? Not that big. Okay, it was in pounds for starters. I actually not calculated what it would be in newtons, but your weight is huge in newtons. You don't want to read that number in newtons because it looks bad. It was 465 pounds. he was big. He was bigger than the average sumo wrestler, but not as big as the biggest ones. So if you are balanced with the same amount on each foot, it would read half of your weight on each foot. But of course, how easy is to get half your weight on each foot? It's pretty hard. But as long as each scale goes up to 300 pounds, my brother was covered. Okay, friction force. A friction force is a force that acts between 2 surfaces to keep them from sliding. And there's actually 2 types of friction we talk about. First, I've got these weights here. I will push on them horizontally, and it's not moving. In that case, we say the force of friction is the force of static friction. Static because the surfaces are not sliding. If I push harder, I make it slide, and then, good job. And then we call it kinetic friction. So kinetic friction when there is motion between the surfaces. Static friction when there's no motion. And you probably are saying, what's the difference? Are you saying that? No?
Yes.
Okay, thank you, Bryce. Bryce is like, what in the heck? Why is the difference? Well, the reason we have a friction force is, number one, and it's something you never think about, there are actually going to be attractive forces between, like, for instance, the molecules in my hand and the molecules on the table. Not that strong, but they're there. Second, there is a conformation. this tabletop is not perfectly smooth. It feels pretty smooth, a lot smoother than asphalt does. But it's not perfectly smooth, and when I put my hand on it, my hand is going to deform a little bit, so it's going up and down with the variations in the surface of the table. If I start sliding, my hand is actually going to have to come up a little because it can't maintain that conformation. You know, it's like if I put my fingers like this, I can have them between the grooves and they won't slide against each other easily. If I want to make them slide, I have to actually cause a vertical separation to make them slide. You have the same thing going on with friction. So if something is stationary, when you push it and want to make it slide, you're actually going to have to put more force because you're going to have to lift it up a little bit before it can start to slide. Once it's sliding, then it's going to have a lower friction. So this has very real ramifications. Let's say you're driving your car and all of a sudden traffic in front of you stops. We all have a panic instinct and we just jam on the brake pedal, right? Well, if you jam on the brake pedal, back in the old days, the tires simply locked up. They don't rotate, and then you have the rubber, which, as you know, asphalt is pretty rough. The rubber is kind of soft. So there's a lot of conformation between the rubber and the road. But when the tires lock up, you start sliding, you don't have that anymore. You have a lower friction. And so you don't stop as quickly as you could if you hadn't locked them up. And furthermore, you have a real problem because you can't steer anymore once your front tires are skidding. So these days, they have anti-lock brakes built into your car. The anti-lock brakes, you jam on the brake pedal because you panic like any normal human does, and the brakes will tighten up until your car senses that the tires start to slip. And then it will release the brakes a little until it stops slipping, and then press down on them again. And so the brakes are constantly pumping, which is why it feels really jerky. But what you're doing is you're having only a little bit of the kinetic friction and mostly static friction. And because static friction is higher than kinetic friction, you have better braking. You'll stop quicker with anti-lock brakes. And plus the added benefit, you can now steer because you have static friction rather than kinetic friction.
Which one's higher?
Static is always higher. I say always higher. In some special cases, they'll be just about the same, but kinetic is never higher. So anti-lock brakes are a very big safety thing. They make you stop quicker and allow you to turn while braking, while braking as hard as you can. Obviously, if you're not locking up tires, you can still turn while braking. It should be noted that if you are a pro-grade driver, you can stop quicker than the anti-lock brakes will. Because the anti-lock brakes are going until it starts to slide, then letting off, and then braking again. If you're a pro, you know exactly what your brakes can take before they'll slide. You can stay at a higher friction than you're getting on average with the anti-lock. But most of us are not going to reach that. Okay, this is a repeat of something we talked about earlier. When Nellie, who is apparently this little purple dressed girl, pushes a crate across a factory floor at constant speed, the force of friction between the crate and the floor is, so she's pushing it along at a constant speed. I'm pushing Amber's drink at constant speed. It's not static.
Maybe equal?
Okay. Equal is correct.
Equal and
It's-
opposite to compression?
It's also going to be opposite. If it was the same direction, go faster, faster, right? Has to be opposite, so they add up to zero because she's going at a constant speed. What if she was increasing her speed? What if she's going faster and faster and faster? What would that tell you about the force of friction? We haven't gotten to this one yet. This is going on what you did previously.
Less opposite push than she pushed.
There was if you're speeding up, there's less opposite push. And if you're slowing down, the friction is greater than her push. I wish this, I'll get it working. Get It may be that I downgraded to a version of Microsoft Office that won't use the pin. I'm worried about that. I talked about Galileo, him dropping the balls, but then I said he probably never did that, drop the balls off the leaning tower of Pisa. What he did was a whole lot of experiments of inclined planes where he had slopes and rolled balls down the slopes. And he rolled different masses of ball and so on. And it was from that he drew his conclusions that Aristotle was wrong, that it's not how much earth you have and it falls at a constant speed, that it speeds up over time. And so we have our current understanding that says if something is in free fall, that means there's nothing opposing its fall. You have the force of gravity pulling it down and nothing else, that it will have a constant, not a constant speed, which I believe is what Aristotle said, but a constant change in speed, a constant acceleration. So the acceleration of gravity, we use G as the letter for it. The acceleration of gravity defines down. And it has a value of, as I said before, the average value at sea level is 9.80 meters per second squared. If you live in San Francisco, that's pretty much exactly the acceleration of gravity. We're slightly different here, but it's pretty close to 9.80 here. Some textbooks use 9.81 so that you have 3 digits in the number. They figure it's just going to be less confusing. Our textbook uses 10 meters per second squared, which is, in my estimation, not a great thing to do, but it makes your calculations much easier. Now, remember from last class period, what does it mean to say meters per second squared?
The time it takes to.
It's the change in speed per the time it takes. Yeah. So 10 meters per second squared means your speed is going to change 10 meters per second every second. So, go ahead.
How long does it take you to reach that speed?
To reach which speed?
To reach the maximum falling speed.
Okay, now Bryson has brought up another topic, which it's good to talk about this. In physics, we make a lot of stupid assumptions. Stupid assumptions because they're relatively true and make our lives easy. So our stupid assumption with falling objects is if it's in free fall, the only thing acting on it, the only thing pushing or pulling, what's another term for things that push and pull? Force. The only force is gravity. But everyone knows, when I was a kid driving from Monterey Bay Academy to Virgil Housel Memorial Junior Academy, now just called Virgil Housel Christian School, I would stick my hand out the window and I'd be going, feeling the air pull back on my hand. Then I'd turn like this and be much less resistance. Anybody else do that kind of stuff when they're a kid? Or an adult? Yeah, I do that too. So I'm feeling that there is a force being applied due to air. We generally call this air resistance. So in our physics class, we completely ignore that. But you know from very practical experience that it exists. And in fact, if there was no air resistance, our cars would get incredibly high fuel economy. Because in the end, if you're driving on the freeway, you basically are trying to overcome the air resistance. So if you make a car so it has less air resistance, you'll get better fuel economy. It's that simple. So there is air resistance. So if I drop this ball, there is an upward force that depends on how fast it's traveling. As you probably notice, going like this, I don't feel air resistance. I have to be in the car moving at a reasonable speed for it to be reasonably strong. And the faster you go, the stronger it is. It's not proportional to speed. It's actually proportional to speed squared if you're going at fast speeds like with a car or with a falling ball. And so the faster you go, the bigger that force resisting it becomes until you reach equilibrium. When you reach the point where the force of gravity downward is equal to the wind resistance upward, then you have equilibrium and it'll just stay in Well, what's the motion going to do once you've reached equilibrium?
Stay
Stay constant.
constant.
You said steady, right?
Yes.
Same thing. So we call that terminal velocity. That's what Bryson was asking about, right? So it depends on things like the shape of this object and the viscosity of the air, how thick the air is. And so you have, different shape to mass ratios will give you different terminal velocity. So if you're jumping out of an airplane, if you spread eagle, your terminal velocity somewhere in the ballpark is 60 miles an hour, which is surprisingly slow. You jump out of an airplane, I said 60 miles an hour. Every number I know is in the metric system for physics. So 60 miles an hour is, if I remember right, something like 25 meters per second or something like that. So if you're accelerating at g until you reach terminal velocity, it would only take about 2.5 seconds. But the fact is, your acceleration is dropping as that resistance force, the air resistance, is increasing. So it's probably going to take longer. We could calculate with some assumptions, but 5 to 10 seconds after you jump out of the airplane, you're going to be at your final velocity. And then you just go to constant speed, whee, until you hit the ground. And at 60 miles an hour, what happens when you hit the ground? Yeah, it's what we call a splat, right? You can, if you're really lucky, survive it. Lucky does not mean hitting water, by the way. Water has a fair amount of inertia. What does inertia mean?
Have you seen the video
Take
with the
mass.
pigs?
And what?
Have you seen the video with the pigs?
No, thank goodness.
No, they're in bags, but they put pigs in a bag and they drop one on the water and one on concrete.
No. No.
You don't see it 'cause it's in a bag and they tell you what happened.
They tell you, when I looked in there, oh, humanity. Yeah.
Pretty much.
Yeah, water has a fair amount of inertia, which is measured in mass, and inertia is the opposition to change in motion. So the water doesn't like to change its motion. Now, if you hit it with a really slow speed like this, your hand just seems to go right in. But if you just go like this, you feel a fair resistance. If you're dumb enough to dive off the diving board and spread eagle onto the water, you really feel it. I broke my tailbone jumping off of a cliff and losing my balance and landing leaning back. Right? That water is pretty hard when you're at speed. 60 miles an hour, you just are going to bounce. And it's not good. So hitting something softer would be better. But there have been people who survive falling from airplanes. How could you make sure you died if you fell from an airplane? We don't want to make, yeah, that's right. If you go head first, you have a lot less area that the air is seeing, hence a lot less air resistance, which means your terminal velocity goes way up. And so you're going to hit the ground at about 90 miles an hour instead of 60 miles an hour. Furthermore, if you're head first hitting the ground, you know you're pitched after that. I won't talk about gruesome stories. As an EMT, we had to learn about people doing silly things. Well, okay. Jumping off of a bridge. Not always the wisest move. There was one case they told us about where the water level was low and it had a lot of mud. And the guy's legs got stuck in the mud. So he drowned. Yeah. And then there's other cases where there was like a post and the guy landed and hit the post. And yeah. I told you about jumping off a cliff. Probably done on my case too. Okay. If a falling object gains 10 meters per second each second, what's its acceleration? Yeah, it's 10 meters per second. You just replace the word each with per second. Why is this answer wrong? It has the wrong unit. You need meters per second squared, and that's just meters per second. That's a unit of speed. The units are super important in physics. Did you have a question, Hosanna?
No.
Okay. Okay, so
Be the right answer.
it is the one he said. Yeah, I'm sorry. I shouldn't have put a box around that one. It was the wrong one. It's what Bryson said, yes. Now, we've been talking about the speed. In lab yesterday, you worked with distance, right? And you related distance with speed. Well, there's an equation we can use to relate the two. And I'm going to write the equation in its full form. Your textbook assumes that you start with zero speed and at zero position for the equation it shows. I'm going to show the full one. So your equation is position. We use x as our symbol for position is equal to x, and we put a little zero to mean at time zero. So your position is your starting position plus v. What does that subscript of zero mean? Starting. Any idea what v means? V stands for speed. And you're like, speed, V? Well, these two young ladies said velocity. Velocity and speed are related. Speed is how fast something is traveling. Velocity is how fast something is traveling with its direction. We call that a vector. And so the V does indeed stand for velocity. But in this case, because I don't have an arrow over it, it actually means speed. So an arrow over it, the V is velocity. Without an arrow, the V is speed. It's how fast you're traveling multiplied by, you probably can all figure out what T is. What is T? Time. Excellent. This thing here, that's a capital delta, Greek letter, and it means change in. So the position is going to be the starting position. I haven't finished the equation, by the way. It's not done yet. Starting position plus the starting speed multiplied by the change in time, the time that's elapsed since you started. Then there's one more term. Plus 1/2 a delta t squared. A, what would A stand for? Acceleration. So that is the equation that allows you to calculate how far something will have traveled based on its initial speed and its acceleration. Now for this table right here, the table is using x0 equals 0 and v0 equals 0. That's where these numbers came from. And it used A is equal to 10 meters per second squared. And so for the distance, since the x0 is 0 and the v0 is 0, we can ignore those first two. And it's just 1/2 the acceleration multiplied by time squared. So if the acceleration is 10 meters per second squared, 1/2 of 10 is 5. And so that final column is 5 multiplied by the time squared. So at 0 seconds, that's 0 clearly. 1 second, 5 times 1 squared is 5. 10 seconds, 5 times 2 squared is 4. 5 times 4 is 20. 3 seconds, it's going to be 5 times 9, it's 45, and so on. So while the speed is increasing in a very simple fashion, the equation for the speed, and once again, I'll show the complete equation for the speed. Much simpler. Since v0 was 0, the speed is just increasing linearly because it's a constant acceleration. 0 seconds is 10 times 0. 1 second, 10 times 1. 2 seconds, 10 times 2, and so on. And so terminal velocity for a falling human in free fall is somewhere around here. But you have to keep in mind that your acceleration is not going to be 10 meters per second squared after the first half second. It's going to start decreasing. So physics class, we just ignore that things would fall at infinite speed or, continually increasing speed. This reminds me, let's just bring up something fun. How many people have watched Mythbusters? Okay. I mean, they were canceled a few years ago, and I know you guys aren't as old as me, so a few years ago seems like a long time you had to ask the question. One of the myths they tackled was the one about what happens if somebody drops a penny off the top of, let's say, the Empire State Building. That's the myth. The myth is you stand down there, somebody tosses a penny off. I think when they did it, they actually did it for the World Trade Center, but obviously that's not been around probably in your lifetime. And so they looked at it. Now that penny, if the penny were to fall perfectly vertically, it would actually reach a very high terminal velocity because there's not much air resistance. But the penny is going to flutter. The penny is going to be going like this. And that gives it a much bigger air resistance. And so their calculation was the terminal velocity for the penny should be something very pedestrian. It'll hurt, but it's not going to kill anyone. But if you watch Mythbusters, you know these guys like to do stupid stuff, right? I mean, why else would you have a TV show? And so they modified a nail gun to shoot pennies. And they made their little dummy out of ballistic gel, and they shot the pennies at it. And they're like, it doesn't stick in very far. Jamie, take off your shirt. And they shoot it with the penny gun. It didn't kill him clearly, hurt a little bit. The funny part is when they were testing the myth that is related to that of throwing playing cards and killing somebody by throwing a playing card and cutting their jugular. You guys heard that one? Yeah, it's apparently an Old West myth about, somebody got mad and playing, getting cheated playing cards, and he threw a card and cut somebody's jugular and killed him. It was murder. So they tested that, and once they determined it's not going to happen, and so they made their card thrower. They got something to stick in the ballistic gel, but they're like, it's not that bad. Jamie, take off your shirt. They throw them at him. Actually had cards stuck in his chest. Why did it stick cards in his chest? Because the cards, if you rotate them, you can keep them from fluttering, and then it's not much resistance, and it has a pretty hard edge. Okay, so that has to do with the reality of physics. It is important to know about the realities. We teach the textbook physics to make the calculations easy, but you have to keep in mind real life.
So in the textbook,
yeah,
if it asks us, or in the homework, it asks us to find, like how long it takes something to hit the ground, do we use those calculations, or do we just add up the...
Do you use the ones that just use the 10 meters per second squared, assuming there's no air resistance? Okay, now, I was going to bring a cup and whatnot, but I forgot it, so I'm going to use my slinky here and a little mass. We hope this works. You guys may or may not have seen this demonstration. If you go to the textbook's website, it has videos to go along with like every section of the textbook. And in this section, Paul Hewitt does the experiment where you set a place on a table very carefully with cheap settings, and then you pull the tablecloth out and the settings stay on the table. You do it with cheap stuff because if you pull wrong, you break everything. Why does that thing work? Why is it used as a physics demonstration?
Because the objects stay in rest.
Okay, the inertia. Objects want to stay at rest. Now, you have that tablecloth that you're pulling out. Is there a force between the tablecloth and the object sitting on it? What do we call that force? Okay, static friction initially. Once you make things slide, it'll become kinetic. So I'll say friction to be generic, but it's starting to state as static. You pull it out, there is a force that's pulling to the side. But there is inertia, a resistance to change in motion. So that's why it changes from static to kinetic when you pull. And if you have a small enough friction and you pull fast enough, if you pull slow, the whole thing's going to move. Because the resistance to change in motion doesn't really matter if you pull really slowly. But if you pull quickly, so there's my slinky, have this in the center. If I pull quickly, it falls in the middle of the slinky because the friction was acting for a short amount of time. It had a large enough inertia that it hardly responded to the pull. So that's what that demonstration is about. It's always cool to see. And good golly, if you deal with a lit flame, you're probably stupid. Right? Because if something goes wrong, because like I said, you pull it wrong and something goes wrong. That would be dumb. So this is a demonstration of inertia. Here's some more demonstration. Okay, that's not it. Here's some more demonstrations, some better than others. The lead ball one is actually a real good one that's safe. The lead ball, you have a lead ball tied to a string to the roof and tied to a string below. If you slowly pull down the string below, you're going to have the force. Now we call this force tension, another force. If I have a string, it will support a force, apply a force that is in the direction the string leaves. So if I look at the ball, the string on top is going to be pulling up. The string on bottom is going to be pulling down. If that ball is stationary, it's in equilibrium. If it's in equilibrium, we know the total forces acting on the ball are going to add up to 0. Well, let's draw arrows for the forces acting on the ball. What forces do you now know are going to be acting on this ball? Okay, force of gravity, which is always down. What else? Okay, that's going to be force tension from the roof, okay? And there's one more. We have a force tension from the, I'm going to put H for hand because it looks more, it doesn't look as close to R as P would. So we have those forces. If those forces add to 0, it's in equilibrium, which one is going to have to be the biggest force? The upward one's going to have to be the biggest because I have 2 down and 1 up. The upward one has to equal the sum of both of them down. So the upward one has to be the biggest one. So if I'm pulling down, I slowly pull harder and harder and harder until I reach the point where the string is going to break. Where's the string going to break? Above or below the ball? Above, because that's the bigger force. But then the crazy thing is if I yank that string real quick, the string will break below the ball. Why is it different with a fast tug versus a slow tug?
When you go with the fast tug, then you're putting too much force from the bottom, and then it's going to snap the ball.
Well, the principle is what I'm looking at. And the principle is the principle of inertia.
That you have to give the ball time to react.
Basically, yes. If I tug it really quickly, the ball doesn't have time to react, so to speak. And so it breaks below. It's the inertia that's making the ball so it doesn't just come down with the tug. And so the tension on top doesn't build as quickly as on bottom because of inertia. So that's a really cool one because it just depends on how quickly you tug the string, which one's going to break. Now, this here is nice, and I'm not even going to talk about it. You guys probably don't have practical experience of getting a hammerhead on a hammer, banging it like this to make the hammerhead tighten up. But it does because you get that metal moving. The handle stops quickly, and the metal's inertia drives it down onto the handle. The one you often see that's totally cool and at the same time pretty dumb is to have a person lie down. I'll lie down on a bed of nails. It just makes it more fun. We'll talk about pressure later. They lie down on a bed of nails, and then they put a brick on their chest. And then they bring out the sledgehammer. And they go whammo, and they hit them with the brick with the sledgehammer. What's going to happen?
Depends on how many nails they use.
Okay, it does depend on how many nails. If there's one nail, they're impaled. I was going to say screwed, but it's a nail, so impaled. Okay, so it depends on how many nails. Let's assume there's plenty of nails, right? That's not part of what I want to talk about. What happens when they hit the brick with the sledgehammer?
Wouldn't the brick break and the person would be fine because there's enough surface area to distribute the force of the sledgehammer?
There is a surface area aspect. We haven't talked about that yet. That once again goes with the pressure, the same idea as the nails. But what I am focusing on is the inertia aspect. The concrete is fairly brittle. It's easy to break, concrete brick. And so when you hit that concrete, the inertia is going to be high enough that you shatter the concrete, and most of the force is going to break up the concrete, and you don't have too much that's absorbed by the person. I have seen cases where people miss getting hit on the chest with a sledgehammer. It's never fun. And so that's another example of inertia. When you see it, you're like, oh, they're going to hit them with a sledgehammer. Just understand there's a lot of inertia in the brick, a lot of inertia in the body. There's not going to be too much. And as Bryson said, the force is spread out over the surface of the brick, so it's not the same as getting hit with the sledgehammer at one spot on your body. All right. We're about done. I like the picture. The idea is it's much better if you have a person on a motorcycle because we can all see the sort of bicycle. I don't know about you, but me and all my friends went over the handlebar once, right? You got to learn how hard to pull that front brake and how hard is too hard. So you have a person in this picture in a car, but in my mind it's a person on a motorcycle, and they're coming up and all of a sudden they're like, I've got to stop quick. They hit the brakes, and the bike stops or the car stops, but the person has a mass, and they were moving, and they're not going to stop instantly. This is a problem in cars. When I was I was on the volunteer fire department and ambulance department at PUC. My first call as an EMT was a guy who had been tweaking for 3 days. He hadn't been asleep. He fell off a ladder. He didn't have a driver's license, go figure. You know. But he gets in a car to drive to his mother's house so she can take him to the hospital. But given that he had been tweaking for 3 days, he fell asleep while he was driving and hit a tree. Now, I tell you all that just to get to the punchline. He wasn't wearing his seatbelt. So he's in his car, and his car stops like this. And what does his body do? It keeps going forward, so he smashed his face into the windshield. My job was to dab up the blood to keep it out of his eyes. My brother was the main EMT, and I was the trainee. And so my job is to dab up the blood. Of course, the guy was on drugs. He's not sure what's going on. It's like, I really messed it up, didn't I? Yeah. What does it look like? Like, well, you're not going to win any beauty contest because you don't want to tell a dude. This is what I wrote. My first ever patient care report. Could not identify his nose. It was just a flat face.
Oh, bro.
Okay, we have seatbelts and airbags and things to help combat that inertia. But without those inertia, the car stops, you don't, wham. All right, that's a good place to break for the weekend, right? Have a happy Sabbath. Don't study on the Sabbath. It's God's gift to you to be able to take a break.